Hi, welcome to today's lesson. Today we're going to be introducing the concept of the discrete random variable. It's just an introduction. Relax. I hope you enjoyed today's lesson. Discrete random variables. What are they? A discrete random variable is a random variable x. Notice this is a capital X. It's not a small x. It's a giant X, which can take on exactly n numerical values. So we define which possible values this x can take on. Each of these values corresponds to one and only one event in our sample space. We call it random because we have no idea which number will come up until after the event has occurred. Here's a very easy example with defining a discrete random variable. With two tosses of a coin, define the discrete random variable as the number of heads. Well, if you flip two coins, you can either get 0 heads, 1 heads, or 2 heads. So we have a probability process where we're defining the total number of heads. We're counting them. The discrete random variable produces a countable number of outcomes. The DRV is associated with the counting process. So if you flip a coin twice, we can count the number of heads you can have. If it goes tails, tails, you have 0 heads. If it goes heads, tails, or tails, heads, you get 1 head. If you go heads, heads, it gives you 2 heads. So this is the process of defining a discrete random variable. Now that we know what a discrete random variable is, let's talk about the symbology that we use and the two principles that are going to govern our work with discrete random variables. We saw earlier that the discrete random variable is this huge capital X. And this capital X can take on different values. For example, the values that were associated with two flips of a coin were 0, 1, and 2. So the probability that X, our discrete random variable, equals one of our values, in our previous example, this would be 0, 1, or 2, is equal to some probability P. So the probability of each of these 0, 1, or 2 for two flips of a coin is designated as small p. That may be the hardest part of discrete random variables, is just getting down the symbology. This is the probability that a discrete random variable equals some specific value is denoted as small p. Here are the properties of the probability function for the discrete random variable. The probability that our discrete random variable equals any one of the defined numbers that we define it as, we could say this is even to xi because we don't know which value we're going to put in there. Each one of these individual probabilities lies between 0 and 1. So the probability that our discrete random variable is equal to one of our values is between 0 and 1. Well, I'm going to have, with two flips of a coin, number of heads, I had 0, 1, or 2. I had 3 different discrete random variable values. If I take the probabilities of each of those, I'm going to get 1. That's what this means. For n mutually exclusive and exhaustive events, for our example, that would be a head value of 0, a head value of 1, or a head value of 2 on two flips of a coin. For all of those events that make up our sample space, E, we saw that as U before with Venn diagrams. It's also known as E, an E written like that. The sum of our individual probabilities is 1. So there's 2 rules you have to know for discrete random variables. One is that each of the individual probabilities is going to be between 0 and 1 inclusive. And then when we sum all of our probabilities up, we get 1. If you can remember those 2 rules, you're going to be fine. Each probability is between 0 and 1, and our total probability is equal to 1. Here's a first example with discrete random variables. A coin is flipped 3 times. List all possible outcomes. Well, I've already made a tree diagram. Heads, tails, and at each branch we have heads and tails. So I get the results, heads, 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 tails, etc. all the way down. Well, X, this is a capital X, this is a discrete random variable. It denotes the number of heads observed. List all the value of X and find the probabilities associated with them. Well, I have 3 heads here, 2 here, 2 here, 1 here, 2 here, 1 here, 1 here, and 0 here. So what are the possibilities for my discrete random variable X? 3, 2, 1, and 0. What are the probabilities associated with each of these? Well, I have 8 possible outcomes, and I have 1, 3. So 3 goes 1 out of 8. For 2, I have 1, 2, 3 possible values. So I go 3 out of 8. For 1, I have 1, 2, 3 values. So I have 3 out of 8. And for 0 heads, I have only 1 possibility out of 8. So I have set up a table here with my discrete random variable, its values defined, and the probabilities associated with each of the values. Note, we have been obeying our two rules. Each of the individual probabilities is between 0 and 1. Our x value is between 0 and 1. And the total sum of these gives us 1, 3, 3, 1, gives us 8 out of 8, or 1, if I add all these probabilities up. So my rules that we saw in our last slide do apply here. Here's our second example involving discrete random variables. Consider the random variable capital X with a probability defined by probability that our discrete random variable equals 0 is alpha, Greek letter alpha. Probability that our discrete random variable equals 1 is 2 alpha, and probability that our DRV is defined as 2 is 3 alpha. Determine the value of alpha. Well, the only two rules we know is that each of these individual probabilities must be between 0 and 1 inclusive, so they could equal 0, they could equal 1, and that the sum of these has got to equal 1. All of our parts together must equal 1. Well, alpha plus 2 alpha plus 3 alpha must equal 1, which means that 6 alpha is equal to 1, so alpha is 1/6. Here's a third example involving the discrete random variable. The probability distribution of a discrete random variable capital X is represented by the function probability capital X is equal to some value, sometimes you see it as xi, is equal to k over x, where x can equal 1, 2, 3, 4, 5, or 6. We've defined our small x to equal 1, 2, 3, 4, 5, or 6. So if small x equals 1, then probability that capital X equals 1 is equal to k over 1. That's how it works. I'm just substituting a 1 in for that x there and a 1 in for this x here. Well, I'd have to substitute 2, 3, 4, 5, and 6. Well, what do we know about discrete random variables so far? We know that if I plug a 1 in here, the probability that my DRV is equal to 1 equals k over 1 is between 0 and 1. We know that. We also know that the sum of all the probabilities is equal to 1. Well, let's use that information to solve our problem. We know that k over 1 plus k over 2, when I substituted 2, plus k over 3 plus k over 4 plus k over 5 plus k over 6 is equal to 1. That's what we know. We know that from our work with discrete random variables. I can factor out a k, and I'm left with 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 is equal to 1. And I won't insult your intelligence, but I know that you can find that our least common denominator is 60, or you could do this on your calculator. And when you solve this, when you divide both sides by this fraction, I would divide both sides by 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. And if I want to get that under one fraction, it's the common denominator is 60 there, and I have to divide by 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. When I do that, I get a k value of 20 over 49. I know that my k, when I solve for k, I get 20 over 49. The rest there is just simple math. Well, using the sum of all probabilities is going to equal to 1, we found that k is equal to 20 over 49. In our second part here, it asks us, find the probability that our discrete random variable is from 3 to 5, including 3 and including 5. Well, our probability function is defined as k over x. So if x is 3, 4, and 5, we're going to have k over 3 plus k over 4 plus k over 5. And now we can do a simple substitution. We just found out k was 20 over 49. 20 over 49 over 3 plus 20 over 49 over 4 plus 20 over 49 over 5. And when you plug this all in, you get 0.34. When using discrete random variables, one of the things we're asked to do is to construct probability functions. This P stands for probability. For example, a bag contains 5 white cubes and 4 red cubes. So I drew a bag here with 5 white cubes and 4 red cubes. 2 cubes are selected in such a way that the first cube drawn is not replaced before the second cube is drawn. So we're drawing without replacement. Find the probability distribution of the discrete random variable x. That's what we have to do, is find the probability distribution. Where x denotes, well, it's a discrete random variable, so it's associated with a counting process. We have to define it. We define it as the number of white cubes selected from the bag. So let's draw a tree diagram. If I select first, I'm either going to get white or red. And then I select again, I'm either going to get white or red. If I select again, I'm going to get white or red. With my first selection, I have 5 out of 9 whites, which leaves me 4 out of 9 reds. We did it without replacement. So if I selected white, I'm left with 4 whites out of 8 cubes left. If I selected white, I'm left with 4 reds out of a total of 8 cubes. If I selected red first, I'm left with 5. I still have 5 white cubes, and there's only 8 cubes left. And if I selected red first, I'm left with 3 reds out of a total of 8. Well, if this is the case, we go white, white here, we go white, red here, we go red, white here, and we go red, red here. If our discrete random variable is the number of cubes that are white, we have 2 here, we have 1 here, and 1 there, and 0 here. So what are the values of our discrete random variable? Our discrete random variable, which is defined as the number of white cubes selected during this process, could be 0, 1, or 2. Well, what are the probabilities? We have to go back to Bayes' law of total probability. The probability of going white, white is simply 5 over 9 times 4 over 8. When you multiply and simplify, you get 5 out of 18. The possibility of going white, red is simply 5 over 9 times 4 over 8, which again is simplified to 5 over 18 when you do that math. The possibility of going red, white is 4 over 9 times 5 over 8, which again is 5 over 18. And last but not least, 4 over 9. Red, red is 4 over 9 times 3 out of 8, which simplifies to 3 out of 18 when you do the math and simplify. Well, for the random variable 2, I get 5 over 18. For the random variable equal to 1, I get 10 over 18. And for the random variable 0, I get 3 over 18. Does this comply with our principles that each of these is between 0 and 1? Yes. And when we add 5 and 10 and 3, do we get 18 out of 18 or 1? Yes, we do. So we've met both of our principles with this problem. If I put the final results in a table form, I see here I've got my discrete random variable, which is defined as the number of white cubes selected in this process. The possibilities for this random variable x are 0, 1, or 2. I found that out in our last pictures. The probability that our discrete random variable is equal to 0, 1, or 2 is defined as 3 over 18, 10 over 18, or 5 over 18. Here is our probability function displayed in a tabular form.